This project begins with data generation using our team's unique identifiers, where all members have contributed the last 4 digits of their student IDs, which will serve as the seed values to construct our system of linear equation in the form of AX equal to B, where these digits will specifically determine the coefficient for our matrix A and the components of our vector B, creating a customized mathematical model derived directly from our team's data.
So for the next slide is seed matrix A and vector B. Each set of the last 4 digits is treated as an integer and summed to obtain the seed value. The total sum is 2875, which is used as the seed in Python. Using the NumPy library, we set this seed so that the random numbers generated remain reproducible. With this seed value, we generate a 3 by 3 matrix A and 3 by 1 vector B, with entiers ranging from -9 to 9. The generated matrix A and vector B are displayed on the slide. This approach ensures that the data is random, yet consistent and suitable for further mathematical analysis.
Next, I will demonstrate how to calculate the determinant of a 3 times 3 matrix using Python's NumPy library, starting with our given matrix A. First, import NumPy, then create the matrix as a NumPy array. After that, use the single command np.lineout.determinantA to compute the determinant, which returns to essentially 323 with the floating point precision, confirming that this matrix is invertible since its determinant is non-zero. Next, I will demonstrate how to calculate the determinant of a 3 times 3 matrix using Python's NumPy library.
In part 2a, I focus on the manual analytical solution of Ax equal to B. Using the matrix A and vector B from the part 1, I first wrote the system explicitly as 3 linear equations in the unknowns factor x1, x2, x3. The equations are equation 1, equation 2, equation 3 as shown below. Writing the system this way prepares it for manual solution using Gaussian elimination, which is the next step to find the values of x1, x2, and x3. In part 2a, I solved the system Ax equal to B manually using linear equation techniques. Writing the system this way make it suitable for manual solution using Gaussian elimination. To solve, I first express the system as an argumented matrix combining A and B. For simplicity, I multiplied row 1 by 1 to make the leading coefficient positive. Then applied elementary row operation to eliminate x1 from row 2 and row 3, transforming the matrix into an upper triangular form. Following this, I eliminated x2 from row 3, leaving only x3 as the unknown in that row. Using back substitution, I solved for x3 equal to 2846 over 2259 and then sequentially determined x2 and x1. This step-by-step manually procedure ensures the solution is accurate and provides a clear foundation for verification. In the next part, Python computation is used to confirm that this analytic solution satisfies Ax equal to B, demonstrating both correctness and consistency. Overall, this approach highlights the systematic use of linear algebra techniques to solve a system of equations accurately. And after performing Gaussian elimination, I proceeded with back substitution to find the unknowns. First, substitute x3 equal to 2846 over 2259 into row 2 to solve the x2. Negative 44x2 minus 31 into 2846 over 2259. So we get negative 6, which simplifies to x2 equal to negative 1699 over 2259. Then substituting x2 and x3 into row 1 allowed me to solve for x1, like showing below as 7x1 minus 4 into negative 1699 over 2259 and then plus it with 2846 overall 2259. So we get answer as 2, giving x1 equal to negative 746 overall 2259. Therefore, the solution vector is x equal to negative 746 over 2259, it is x1. Negative 1699 over 2259, it is x2. 2846 over 2259, it is x3, and this x is in 3 times 3 formula. Next part, A.3, to To ensure the system has a unique solution, I calculated the determinant of matrix A using the standard 3 times 3 formula as showing below. Determination of 3 times 3 A matrix. So we get answer as 323 by calculating. Since determination A not equal to 0, the matrix is invertible, confirming that the system has a unique solution. Finally, I verify the solution by substituting the values of x1, x2, x3 back into Ax. The resulting vector Ax equal to negative 2, negative 2, and 8 matches the original vector B, confirming that the analytical solution is correct.
For part 2B, I verified the correctness of analytical solution using Python in Google Colab. First, I defined the coefficient matrix A and the constant vector B exactly as given in the question. Then, entered the analytical solution vector X, which I obtained in the previous part using mathematical methods. To verify the solution, I compute the matrix multiplication AX using Python NumPy library. This allows us to efficiently perform matrix operation and avoid manual calculation errors. After running the code, the compute result of AX is negative 2, negative 2, 8, which matches the original vector B exactly. Since AX equals B, this confirms that the analytical solution satisfies the equation AX equal to B. Therefore, the solution obtained earlier is correct and has been successfully verified using Python. This step demonstrates how numerical tools like Python can be used to validate analytical solution accurately and efficiently. More than that, let me further prove that solution is correct by showing the step-by-step calculation for better understanding. We start from the matrix equation AX equal to B. Step 1, I write down the coefficient matrix A and the solution vector X. The matrix A is a 3 times 3 matrix and X is the analytical solution obtained earlier expressed in fractional form. Next, I perform the matrix multiplication row by row. For the first row, I multiply each element of the first row of A with the corresponding element of X and then add the result. This simplifies to negative 2. For the second row, I repeat the same process. After simplify the fraction, the result is again negative 2. For the third row, I multiply the third row of A with the vector X. After simplification, the result is 8. And then combining all the three results, we obtain AX equal to negative 2, negative 2, 8. This is exactly the same as the given vector B, negative 2, negative 2, 8. Since multiplying the matrix A with the solution vector X gives the original vector B, this confirms that the solution is correct. In this part, I will clearly explain the output included in my report as already demonstrated in part 2. First, the output label compute AX represents the result obtained by multiplying the coefficient matrix A with the solution vector X using Python. This calculation verifies whether the solution satisfies the equation AX equal to B. Next, the output label original B refers to the constant vector given in part 1 of the equation. This vector represents the right-hand side of system of linear equation. When we compare these two outputs, we can see that they match exactly. This exact match confirms strong agreement between the manual analytical solution and the Python-based verification. Furthermore, the system AX equal to B has a unique solution because the determinant of matrix A is not equal to 0. In this case, determinant A equal to 3 to 3, which confirms that the matrix is invertible. The manual analytical solution was obtained earlier using Gaussian elimination, performed step by step to ensure accuracy. Finally, both manual substitution and Python verification confirm that the solution is correct and accurate, providing strong confidence in the final result.
Now I'm repeating part 3a, which is the manual Jacobi iterative method. The Jacobi method is the numerical technique used to solve a system of linear equations of the form Ax equal to b, especially when solve it directly is difficult. C1. Derivating the Jacobi interaction formula. So we are given the matrix A and vector D. the system we want to solve is Ax equal to b, where x consists of x1, x2, and x3. From the first row, we have negative 7x1 plus 4x2 minus x3 equal to negative 2. We rearrange this equal to solve for x1. So x1 equal to negative 2 minus 4x2 plus x3 divided by negative 7. From the second row, we have negative 4x1 minus 4x2 minus 5x3 equal to negative 2. We rearrange these equations to solve for x2. So x2 equal to negative 2 plus 4x1 plus 5x3 divided by negative 4. From the third row, we have negative 3x1 minus 2 minus x2 plus 5x3 equal to 8. We rearrange this equation to solve for x3. So x3 equal to x plus 3x1 plus x2 divided by 5. Using the Jacobi method, we compute the next iteration using only values from the previous iteration. So we write x1 at k plus 1, x2 at k plus 1, and x3 at k plus 1. Each new value depends only value from iteration k, not the updated ones. Okay, so part for C2 initial guess. According to the project requirement, we choose the initial guess x at 0 equal to 0, 0, and 0. This means all variables start from zeros. C3 manual computation of the first few iterations. Now we compute iteration 1 using the initial guess. Sub the zeros into the formulas. x1 equal to 2 divided by 7, which is 0.2857. x2 equal to 1 divided by 2, which is 0.5. x3 equal to 8 divided by 5, which is 1.6. So the first iteration result is 0.2857, 0.5, and 1.6. So next is iteration 2 using the value from iteration 1. After sub the values and calculating, x1 equal to 0.3428, x2 equal to negative 1.7857, x3 equal to 1.8714. So the second iteration result is 0.3428, negative 1.7857, and 1.8714. Repeating the same process for iteration 3, we obtain that x1 equal to negative 1.002, x2 equal to negative 2.1821, x3 equal to 1.44x6. From the iteration table, we can observe that the values do not settle down to a fixed solutions. This indicates non-convergence. C4. Why the Jacobi method does not converge? Jacobi converges only if the matrix is strictly diagonally dominant. This means the absolute value of the diagonal element must be greater than the sum of the absolute value of the other elements in the same row. For row 1, we check 7 is greater than 5, which is true. For row 2, we check 4 is greater than 9, which is false. So row 2 false diagonal dominance. For row 3, we check 5 is greater than 4, which is true. In conclusion, since row 2 is not diagonally dominant, the matrix is not diagonally or dominant over row. Therefore, the Jacobi method does not converge, and this divergence is mathematically expected.
Firstly, my name is Akil and I will explain part 3b, starting with the implementation. We implemented the Jacobi iterative method using a Python. The same matrix A and vector B from the previous part we are used. The initial guess was set as at 0 equals 0, 0, 0. Overall, the code calculates the approximate solution at each iteration. Moving on the iteration process, during each iteration, the Jacobi method updates each variable using values from the previous iteration. In this implementation, the process was repeated for 3 iterations only. This was done to observe the behavior of the Jacobi method.
So guys, after that, the result obtained from the Python were compared with the manual Jacobi method and the analytical solution. From the comparison, we can see that the values change significantly between iteration instead of approaching a stable solution. This indicates that the Jacobi method does not converge for the system, and the numerical results different from the analytical solution. This highlights the limitation of using the Jacobi method for this particular system of equation. So guys, finally, The difference between the Jacobi result and the analytical solution is expected. This is because the coefficient matrix is not strictly diagonally dominant, which is a key requirement for the Jacobi method to converge. As a result, the iterative values diverge instead of approaching a stable solution. This indicates that the Jacobi method is not suitable for this system. Hence, the divergence observed is mathematically justified and consistent with theoretical expectation.